When we work on the Norton circuit or Thevenin circuit, always you are asked to find V naught, I naught given in one of these registers. So this is I naught. We're going to find VTH first. First thing you need to do is taking out I sub naught. That's what we want. Okay, that's the load. Take the load out, and then we're going to replace that as VTH. When you write VTH any given node, always top is the positive, the bottom is the negative. If it's somewhere in the horizontal one, then left side is a positive, right side is a negative. Now, we need to just find the VTH in this circuit. How? Any suggestion? So in this circuit, find the VTH. We may want to do the KVL in here, right? We know the voltage, and if you can calculate the voltage across here, we should be able to find VTH. Current division? No, again, current division, we can apply one current source with the clear two parallel resistors. So in here, no, because these two are not parallel, right? And also there is a voltage source, so no. Yeah, 2 milliamps. Where is going? 2 milliamp. It's gonna go through 3K. V equals IR. That's it. Right, this is open circuit because we took that out. And this current is now go only way through here. So we can simply find the voltage across here. And that is 6 kVL. There, negative 12, negative 6 plus VTH equals to 0. VTH equals to 18. All right? Current goes higher potential to lower potential. So we need to put the polarity this way. And then when you do KVL, entering negative terminal, positive terminal, that's what is negative 12 minus 6 plus VTH. That's it. This is actual current assigned to going in that direction, right? So this is given. We cannot change that. This is the positive 2 milliamp. And that is entering the higher potential to lower potential. So voltage has to be positive and negative always. So you need to remember two things in the given circuit. So when we have the single loop, it's a higher potential to lower potential. That makes sense because polarity of this guy has to be higher potential to lower potential. Since they are parallel, has to be 5, right? And then when you do KVL, 5 minus 5 equals to 0. So those are the two things. Current go in that direction, and then polarity of those two. So find the VTH. We have VTH equals 18 volts. Now we need to find RTH. To find the RTH, we have to use the superposition method. So I'm going to use this guy. We took this guy off, still same thing. And I'm going to write this as RTH instead of VTH. And then in the superposition, what do we do in the voltage source? Short circuit. And what do we do with the current source? Open circuit. Our objective is to find equivalent RTH, total resistance, based on what we learned in the superposition. When we have an independent voltage source, make it short circuit. Independent current source, make it to open circuit. Now, I'm standing right there, and we need to figure it out, the equivalent resistance by looking at here. So this 2K and 4K, they are series, so we can combine these two guys. So this is the node, and what about these two guys, 3K and 6K? In order to identify all of those, we need to find the nodes, right? I'm gonna just call it node A and B. So it's nothing. 3K, this guy has A in the left hand, right hand is RTH, but 6K is a B and A. So 3K and 6K, they don't have any relationship. No parallel, no series. Are we okay with that? Okay. Now, what about this 6K with this short circuit? His left hand is B, right hand is A. This short circuit, left hand, right hand, they are parallel, right? Do you see that? 6K versus this short circuit. Therefore, we can simply ignore that because that is the parallel with the 0. It's going to be 0. Now, by looking at from RTH, this is just 3. So this is how we find RTH is a 3K. So it's a little bit tricky, find the RTH, because just like what we learned from superposition, we need to turn off independent voltage and current sources. Therefore, our Thevenin circuit is going to be plus minus VTH, which is 18 volts series, and this is RTH, that is 3K, and our load that we took that out is a 6K, and the current going downward. So I sub 0 is what? V18 over total R 9K, that is 2 milliamp. Yes, so when we do this finding RTH, we need to assign the node. Here's the node, here's the node, here's the node. And now, first thing we want to do, we want to look at, is it the parallel or series, 3K and 6K, so that we combine them. But it's nothing in here. And at the same time, when we look at it from node A to B, so no resistance, it's what we call short circuit. It's a highway, and that is parallel with this 6K. So if we redraw the circuit, we have, this is C, we have C here, and then B here. This is our RTH, and then there's a somewhere here. So A to C, this guy, and then we have B to C, this guy, and then A to B, there's a short circuit, and also A to B, there's a 6K. Since these two are parallel, so that's just gonna go away. Good? Now, we just found the Thevenin circuit. Now let's find the Norton circuit. So in the Norton circuit, we're gonna do the same thing for RTH. So we already did it, so we don't have to do it. So RTH, also called R sub N, which is 3K. We're gonna use that. Now what we need to do, we need to put back voltage from here to here as a 12 and 2 milli, 4K, 2K. Okay, so in the voltage VTH, we took this out and put the open circuit and saying VTH, right? For Norton, what we need to do, we need to take out and assign I sub N downward. Take this out, make a short circuit. Always the Norton current going downward, always downward. So what do? When you look at this circuit, especially for when we add the short circuit, what's going to happen to the circuit? It's a short circuit. Therefore, the current go here and hit this node. What's going to happen? Yeah, going down, right? Do you see that? So we know this 2 milliamp, when you hit this, it's going to go down. But there's an additional current go through here and going down. But in this loop, when you do the KVL, some of the voltage has to be 0, right? So negative 12, therefore this has to be, so it should be plus minus 12. Has to be. Do the KVL, as it's sum of the voltage equals to 0. That means, what's the current in here? 4 milliamp. So what is I sub N? 6 milliamp. Before you apply node analysis, mesh analysis, take a look at the circuit, see whether we can use just V equals IR. So in this section, always when we find I sub N, we're going to have short circuit. When you find the voltage, we're going to have an open circuit. So most likely there is a easier way to calculate I sub N VTH. Once we have that, now the Norton circuit is going to be always going up as a I sub N, which is equal to 6 milli, and then RTH equals 3K, and then add our load, that is 6K, and current that we want to find is that. Now we can use current division in here. Current division. So the opposite I sub 0 equals the opposite 3K over 3K plus 6K times 6 milli. So that is 3 over 9 times 6 milli. Let's do the node analysis here. So let's just review for the exam. Let's see, we can find the I sub naught as 2 milli. We have node as, I'm going to call it 12. I'm going to call this guy as V naught. And this is V1. Then assign the direction of the current. We have here this direction there, so maybe here. Entering 12 minus V0 over 3K plus 2 milli, and leaving V0 over 6K. So we're gonna multiply everywhere by 6K. 24 minus V0 plus 12 equals to V0. Move it over. 2 V0 equals to 12. The 36. Yeah, thank you. KCL minus 2 V0. And this guy should be 3 now, right? And then 36. So V0 equals 12 volts. This is way easier than Norton Thevenin, right? And V0 is 12, so I0 equals to V0 over 6K. So V0 is 12 over 6K, which is 2 milliamp. Always you can check your answer using different method. Now, mesh analysis. Okay, let's do the mesh analysis. It's a super mesh. Let's do that. We're gonna have I sub 1, so mesh current. Here's I sub 2, mesh current. I sub 3, mesh current. 2 milliamp, the current source in between two mesh current. So we need to do super mesh. So the super mesh is gonna be going this way. Okay, so K, this time VL at super mesh. So we have a 4K times I sub 3 plus 2K times this guy, I sub 2 plus 6K times this guy, I sub 2 minus I sub 1, and then 3K. This time going in that super mesh in that direction, so I sub 3 is positive. I sub 3 minus I sub 1 equals to 0. So let's collect the I sub 1. Negative 9 I sub 1. I sub 2, we have 2K, 6K plus 8K I sub 2. And then I sub 3, 3K and 4K plus 7K I sub 3 equals to 0. And then this mesh, so KVL using I sub 1, we have 3K I sub 1 minus I sub 3 plus 6K, we have I sub 1 minus I sub 2 equals 12. So that is 3K, 6K, positive 9K I sub 1, I sub 2, negative 6K I sub 2, I sub 3, negative 3K I sub 3 equals to 12. So we have one equation and the second equation. And then we should have one more equation, right? We need to do KCL using this guy. So best place is going to be here because this is I sub 3 and this is I sub 2. So KCL at node A, then entering I sub 3 equals leaving I sub 2 plus 2 milli. So from here, now we have I sub 2 minus I sub 3 equals to negative 2 milli. We have three equations. Okay, so plug it in your calculator. 8 over 3, 2 over 3, 8 over 3 again. Okay, now when we do KCL at V, we have I sub 2, and this is I sub 1. Therefore, when we do KCL at B, entering I sub 2, which is 2 over 3, and plus entering I sub 0 equals to leaving I sub 1, which is 8 over 3. So I sub 0 equals 8 over 3 minus 2 over 3, which is 6 over 3, which is 2 milliamp. That's what we found. Yeah, and the super mesh, right, because this independent current source is between I sub 2 and I sub 3. I sub 1 is itself, so there's no current source, so that's what we did, KVL I sub 1. If we have the current source in here, then we're going to have a super mesh in here. if this current is here, we're going to have super mesh including I sub 1 and I sub 3. So we want to find RTH first this time. So we're going to take this out because we will need to find I sub 0 right there. For RTH, we need to have the circuit. This guy is open circuit, open circuit, open circuit. So we have this time is really straightforward. So RTH, Rn equals 3K. Now find the VTH. So we need to say here, VTH, positive, negative. Any suggestions? Right, over there, right? Go through 2 kilo ohm. There's 4 milliamps going into this node, 6 milliamp going into this node. So obviously, 10 milliamp is gonna go in that. Therefore, positive, and then 10 times 20, negative. Now, in order to find the VTH, we're gonna do KVL again in this loop. We know the voltage now. We need to find the voltage across here. That's our job. How? So we have 2 milli going up, but here is 4 milli. That means we have to have 2 milli going into that node. That way, 2 milli, add them up, 4 milli going around. And we're actually going into 10 milli in this node. Therefore, current going downward is going to be 8 milliamp plus 8 volts minus. Now we need to do KVL in here, then negative 8, negative 20 plus VTH equals to 0. Therefore, VTH equals 28 volts. Therefore, our Thevenin circuit is going to be VTH series with RTH, and the load that we took that out, that's the 1K, and we need to find I naught equals V over R. V is 28 over R is a 4K, 7.